All right, this session is recording now. So, welcome to the fourth weekly problem solving session for the Physics of Nanoscale Devices NPTEL course. My name is Jyotishwaran. I'm a PhD student from the Electronics and Communication Engineering Department of IIT Roorkee. So, to begin, in today's session, we shall be spending slightly over half the time with the Fermi-Dirac distribution and the Fermi distribution function. So essentially, whatever parts of discussion that I kind of left out from last session, I will carry on from there and consider some example problems. And then we will quickly move on to the basic ideas of the ballistic transport model. So, and mostly there are going to be only derivations in the second part. So we'll go through the things. So in the first part, we are going to look at the significance of the Fermi distribution. This is something I wanted to discuss last week. However, I was unable to, because more time was spent on other topics, I was unable to cover that. So in today's session, we should look at that. And then we shall discuss the notion of Fermi levels in solids and the effect of doping on the Fermi levels in solids. And similarly, when we look at the ballistic transport model, we'll essentially combine the notion of Fermi levels with that of density of states and look at the different properties associated with a nanoscale channel. So again, the part about modes is something that I shall only mention in brief. So we shall not be dealing with modes in detail. So this is only an intro. Modes will be the central part of the discussion in next week's session. Okay, so yeah, let me begin the session in earnest. In fact, let me make a new slide. So yeah, there were a couple of things that. Oh, yes. So Fermi Dirac distribution. So let us call this the recap from last week. So the first thing, first and foremost, we saw the form of the Fermi function, which is equal to this 1 divided by 1 plus exponential e minus af divided by kbt. Sometimes ef is represented as mu. So these things were discussed. And I think I misspoke when I spoke about the significance of this. So what does this function represent? So this function essentially gives me, of course, it's a probability density function. So I know this is a probability density function. But the most important thing is probability of what? So the Fermi-Dirac function, the distribution function, gives us the following. The probability of any electron, or I shouldn't say any electron, the probability of an electron in any system having energy in the range E to E plus D is given by f of E dE. So this is the point. Like the Fermi distribution function is the same for any system. My system can be a classical system. My system can be, well, not, let us not say classical. So my system can be a macroscopic system. It can be a microscopic system. There may be quantum confinement. There may not be quantum confinement. Regardless of all of those factors, the probability of an electron to have energy in the range E to E plus D is given by this expression. So the Fermi-Dirac distribution is a system-independent f of E, okay, is E plus D at a given temperature. So at temperature T. So this statement will become more clear when we look at one of the examples. So this is the definition. So the Fermi distribution function is defined for electrons. It is not electrons in a solid or electrons, as a part of a plasma or electrons elsewhere. The whole idea is this is a fundamental property of the electrons themselves. So when I'm writing E here, this may be continuous. I mean, in principle, E is always continuous when I'm writing f of E. But when I'm considering different systems, depending on the degree of confinement, there may be discrete energy states or there may be continuous energy states. And in certain cases, we may have a mixture of both. We may have a mixture of continuous and discrete energy states. And that is typically how systems occur in nature. But regardless of all those factors, f of E just gives me the property that an electron at a given temperature will have this much probability to have an energy in the aforementioned range, E to E plus D. Okay, so this is something I believe I did not convey properly last week. So, what are the implications of this? The implications are as follows. So, first thing, shall I, why not? I'll just make a new slide and say, and I'll say implications of, or rather than saying implications, I'll say, what should I say? I'll say nothing. I'll just write these as points. These aren't like so unique that they need a separate title. So the first thing, what are the, yes, I can say applications, yes. So, okay, fine, I have this distribution. Oh, no, no, no. Sorry. So, yeah. So the applications of the Fermi distribution. So the first one is, what's happening? Yes. The first thing that I can derive is this probability of excitation. So what does this mean? So let us say, and let us say electron goes from energy level E1 to E2. So let us say I have a system, not let us say, so to say, I have a system like this. Let me consider it having two energy levels, E1 and E2. Now, given that an electron is present in this state, if I were to ask the question, what is the probability that the electron gets excited from E1 to E2 on its own? Okay, goes from energy level E1 to E2 on its own. So when it's okay, it's technically not on its own. I should be more accurate here. E1 to E2 through thermal excitations. So what is thermal excitation? So whenever I place any material in a finite temperature environment, the material will exchange some energy with the environment. It will either dissipate energy into the environment or it will absorb energy from the environment depending on the temperature difference or the configuration of the system. So this is something that has been observed since, like, I mean, it's common sense. Like if I place any object near a heat source, it is likely to get heated. And that heat is essentially transferred as energy from the heat source to the material, where the individual particles in the material gain some energy. So now this essentially is identified by, now I'm not saying that the system has only one electron. Okay, the system has many electrons. So I will also mention two or three things here. So not one or two things here. So first, the system contains many electrons. E minus, and the second thing is I will only consider the case where t is greater than 0. Okay. We are right now, we shall not look at t equal to 0. T equal to 0 we'll look at in a minute. Okay, so now if I were to ask what is the probability it goes from here to there, that excitation can happen if and only if E2 is empty. So that is the first point. So excitation can occur if and only if E2 is empty, which implies there is no electron in my system which has energy E2. Like these are not energy levels of the system. This is just, I can think of it independent of the idea of energy levels, because if an electron anywhere has a certain energy level, then due to Pauli's exclusion principle, no two electrons can have the same energy, can exist in the same state at the same place. So if and only if, yeah, this state E2 is empty. Now, which implies the quantity that I will have to measure is 1 minus f of E2, because f of E2 will tell me the probability that an electron has an energy in this range. Now, if I need to have no electrons in this range, then I need to take 1 minus this quantity. Essentially, it's, the probability of the complement of the given event, the negation of the given event. So this is the probability of excitation. So probability of excitation is equal to this quantity. Okay. So this is the primary, or not primary, the most direct application of the Fermi distribution. We will see many more during the course of this session. So yes, now the first important property for the Fermi-Dirac distribution is the Fermi function has a symmetry. So what is the symmetry? The symmetry is like this. So if I were to consider and well, just for the, again, for the sake of completeness, I will say one more thing. F of E is always greater than 0. This function can never have a negative value for any value of energy, positive or negative. And we are, okay, here I will also mention that E is greater than 0, because typically that is how we define our system. Okay, so you know what? E need not be greater than 0. It is fine. So E can be negative also. There is no harm in E being negative. So f of E will always be positive and it can never be greater than 1. So this quantity, like much like a probability distribution function, will always be in this range only. Well, technically it can also be zero, but that is asymptotic. I can never find a point on the axis where it will, hit zero. Okay, so unless I have some exceptional circumstances. Okay, so now my Fermi distribution function will be something like this. So this point, okay, should be okay. Why not? So this point is going to be my Fermi energy EF. The axes are labeled as E and F of E. So since it cannot be greater than 1 at the lowest point, not lowest point, at the zero energy, the function is going to have value 1. And as it goes further and further for some, for very large E, it will tend to 0. Now at this point, yesterday I mentioned that the Fermi distribution function will have a value of 0.5 regardless of the temperature. So the symmetry is this: whatever value of the function I measure at some point over here, which is, let us say, EF minus delta or EF minus some E, if I move the same direction to the right of EF and arrive at EF plus E, then the value of the function that I will get will be 1 minus the value that I get at this point. So this is a kind of an inverse symmetry of the Fermi distribution function. So from this, what we can say is the following. So if I were to consider f of EF, so this implies, yes, this implies f of EF should be equal to 1 minus f of EF when I like set E to be 0, because for any interval this symmetry holds. So if I set the interval E to be 0, then f of EF should be 1 minus f of EF, and therefore f of EF is equal to half. We have a new attendee joining us. So f of EF is half. So yes. Now, if I'm talking about this Fermi level, then this Fermi level is given by, I mean, of a given system not depend, only on the available energy states and the number of particles occupying the system. So, in the strictest sense, the Fermi level is a system dependent, like I shouldn't say system, yes, it is a system dependent quantity. To be more precise, the Fermi level is something that defines the system. So the number of energy levels I have and the number of electrons that are present, these two together will uniquely fix the Fermi level for that system. That Fermi level will shift if and only if either of these change. If the energy levels change or if the number of electrons change. Okay. So available energy states, and or to be more precise on the value of the available energy states, and number of electrons, number of particles. So only if either one of these change, the Fermi level will change. For no other parameter will the Fermi level change. So in general, increasing or lowering the temperature will not change the Fermi level of a system. Increasing the pressure or any other parameter, physical parameter, will typically not change the Fermi level unless and until it ends up either changing the value of the energy levels or it changes the number of particles present. Okay, so now let us look at the. So this first part was done in last week. So this was done last week, and So you can just go ahead and refer to that, and the answer will come out to be something like 6.7% or something like that, thereabouts. Okay. Now, yes. Now the question is, we are considering an electron that is at an energy level 5 kBT below the Fermi level. So let me redraw. You know what? I can just copy that thing here. And I will paste it here. What's happening? Did I not select the whole thing? Okay, let me select it like this then. Yes. So now essentially we were at, in the case where E is equal to, no, 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 I don't want this. Yes. The case where E is equal to 5 kBT. So we were somewhere like we are at this point where the probability is given to be 5 kBT above. But yes. Uh, so we are over here actually. We are at this point plus 5 kBT. So the probability of an electron having that much energy is around less than 7%. Now, the second question was to comment on the probability that the electron with the that an electron with an energy below the Fermi level can undergo excitation. So the question that is being asked is, for any electron that is below the Fermi level, for it to undergo any kind of excitation. Now, again, what is the condition prerequisite for any electron below the Fermi level to undergo excitation? The energy level to which it is getting excited should be empty. So for that to be empty, I need to find out the excitation probability, which is given by f of 1 minus E2. So from that, what we will essentially get is the following. So we will have, so excitation probability will be equal to summation EI. Let us say the electron has an initial energy E naught. E naught. Then EI is equal to E naught all the way till infinity. The probability of all of the other states being empty, which will be given by 1 minus f of EI. Now, I told that this quantity E is typically treated as continuous. So, in the continuous limit, it can be written as an integral starting from E naught to infinity of 1 minus f of E. I don't need this parenthesis over here. dE. So I have this integral over here. Now, how do I evaluate this integral? For that, we need to remember the property that integral 0 to infinity f of E dE is 1. So the integration over all energy values is defined to be 1. It is set to be 1 because I'm integrating over the entire range of possible energies, and I'm integrating a probability density function. Therefore, the answer I will get is
I
One.
had a doubt. Can I
Yeah.
ask?
Yes, yes. Please.
Sir, like this Fermi distribution changes with temperature, right?
Uh,
Like the Fermi level. The
no,
Fermi
the
level
Fermi
was
level does not change. Okay, you joined just now. So let me go back and talk about this. So the Fermi level of a given system depends only on. I have a keyboard. Why did I do this? So depends only on the value of the available energy levels. So available energy states and their
this
values.
occupation will
Huh?
these occupations of electrons in these states will get rise by temperature.
Okay. Yes, while what you are saying is technically, or rather, let me just reconfirm. What you are trying to say is, as the temperature increases, are you implying that the energy of the electrons will increase? Or are you saying the energy levels will move with temperature? Which are you saying?
Energy of electrons.
Energy of the electrons will increase. Of course, the energy of the electrons will increase, but I don't care about the energy of the electrons. I care about the available energy states in my system. So the question you need to ask is, if I increase my temperature, will this change? Of course, the average energy of my electrons will go up. Like that is the whole point of temperature. But that
Yeah,
does
but
not define
the
the.
energy levels won't change. Yeah,
Yeah.
is that
So as long as they don't change, the Fermi level will not change. I will give you an example right now. Like we'll solve them as problems, and then they should make more sense. Let me just and their not values and their energy values and the number of particles. Yes. So yes, I will just erase this. What is happening? Have I switched displays? No, I don't seem to have. Can I write here? Yes, I can. Then why can't I erase this line? No, I can. Good.
can we say this Fermi level is like a virtual level in between
It
the
is like a
bands? Virtual level, like this will
not
tell some
necessarily. It
changes.
can also be a real energy level. We will see an example for that. Um,
But
I will write
suppose
another definition that I discussed last week. So an alternate definition of the Fermi level is this. So the Fermi level,
so it doesn't depends on like people write band diagram and there won't be any allowed states in between the gap of conduction valence band. But somehow like
I will
Fermi,
cover that exactly in a problem. So
yeah,
just
perfect.
stay with me for a few minutes. Another definition for the Fermi level is this: the lowest possible energy an electron needs to have to be needs to have in order to be yes not to be needs to have in order to be added to a system of electrons. Like wherever I say electrons, you can replace it with fermions. Okay, but since the only fermion we are going to talk about is are electrons, so system of electrons at t equal to 0 Kelvin. The lowest possible energy is an electron like may have. I don't even say needs to have. May have. So this is essentially the definition of the chemical potential. Like if you're familiar with some thermodynamics, you know that the lowest possible energy a particle needs to have to become a part of an existing system, already existing system, is known as the chemical potential. And the Fermi level is nothing but the chemical potential for fermions. Okay. So we'll see what these terms mean right now. Let me just solve this
So
problem.
is there any difference in like between chemical potential and Fermi energy?
No, for fermions, they are the same quantity. They are just two
Yes.
alternate names. Like that's what I said. The Fermi level is the chemical potential for a system of fermions.
Okay, thank you.
Yeah, you're welcome. So, so it is yes. So the excitation probability is given by this quantity. I know this is equal to 1. So since 0 to infinity integration is 1, this integration is going to be equal to 1 minus integral 0 to E naught uh, no, no, no. E naught to infinity 1 minus this is equal to 0. So what I can do is I can add that integral and that should be equal to 0. That will also be equal to 1. Uh, what was I about to write here? So I know this quantity is equal to 1. So from here I can say this quantity minus this quantity is 1 and this is integrating a constant. So this is going to be how was I supposed to write this? Oh yes, yes. So this implies this further implies integral 1 minus f of e. Now this may not look so straightforward. There is a reason for that because this quantity dE, like this is not a straightforward Riemann integral. So this is not, I'm not just integrating this function with respect to E. This integral also has some other significance. Like if I were to look at this directly as the area under the curve, then, and I say that it already has a height of 1, then if I'm integrating from 0 to infinity, then this quantity should, have a very large area under the curve. So I'm not naively integrating here. This quantity d is kind of a loaded quantity. Okay. So in that case, integral 0 to infinity of this is going to be 0. So from this, I can just say this is 1 minus this quantity, or rather, this is equal to minus 0 to E naught. Not minus, it's going to be plus. F of ED, wrong color. Yeah, F of E D. So this tells me the excitation probability for any electron below the Fermi level. So if I set E equal to EF, we will again see that this quantity will become half D and half D here. So I will end up getting the value half. So any constant integrated with respect to this curve will give me the same value as the constant. Like I should not write it as half into E. So these integrals are not straightforward integrals. We shall discuss more about this, some maybe a couple of weeks down the line. Because again, I let me repeat, if I directly look at it as the area under the curve, then wherever E equal to 1, I should get area 1. However, this is actually the quantity that is equal to 1. So the Fermi distribution has an inherent measure associated with it. And I do not want to discuss measure theory in this course because that will be way too much mathematics. Suffice to say, you can trust me and take this to be the quantity that gives me the probability for excitation. So 0 to E naught. Okay. Yes. All right. Yeah. So now we have, yes, now the following questions. So first is sketch the Fermi distribution for a function at t not equal to 0. I've already done it twice before. So, we are not going to repeat that. So the first part is done. Okay. And so this is done. Oh, no, no, no. So this is okay. This is for a material. So we have to do this. So now, how does the Fermi level associate to a particular system? Because as I mentioned in the very beginning of today's discussion, the Fermi distribution is defined for every system. It is defined for any system as the same. So what changes when I move from one kind of a system to another? The thing that changes is, so the system properties. So let me just write it over here. So Fermi distribution, Fermi function does not depend on a system, on a system. The Fermi level depends entirely on the system. But it does not give me any special information about the system. The thing that gives me the actual information about the system as to how many sorry how many energy levels I have at a given value of energy, that comes from the density of states. That comes from the density of states. This contains details of the energy levels. So let us consider a simplistic solid where I have a valence band and a conduction band. They are not overlapping. No other special properties are observed. This is a simple valence band and a conduction band which is separated by a band gap. Okay. So I have, yes, this kind of a system here, and I will have my valence band above, sorry, my conduction band, my conduction band will be something like this. Please forgive my inaccuracies. And just for a variety of color, I will have a valence band that is like this. These curves need not be symmetric, as you may have noticed from the chronic penny model. And then another thing is, so I will have so EV over here and EC over here. So this is the system. Now we need to sketch the, like, mm, observe the symmetry property of the Fermi distribution function. Like whenever I define the Fermi function, I have to make sure that this symmetry property is always satisfied. This is always satisfied in any system. Okay. So now the first thing that we know is, so yes. So the first thing that is given is that for this system, the valence band is completely filled at t equal to 0 Kelvin. So what happens at t equal to 0 Kelvin? So at t equal to 0 Kelvin, all levels below the Fermi level below the Fermi level are occupied. and all levels above the Fermi level are empty. And I have been given that in this system at T equal to 0 Kelvin, the valence band is completely filled. So now how do I go about defining the Fermi distribution function? Like where will the Fermi level lie? That is essentially what I'm asking. So at T equal to 0 Kelvin, the Fermi function is going to be a flat line up to the Fermi level, and after that it is going to drop to 0. So that is the significance of the T equal to 0 Kelvin. So now you can see the definition of the chemical potential version definition of the Fermi level. So to this system, if I need to add one more electron, my energy has to be at least as high as the Fermi level, because all other levels below that are fully occupied. I cannot insert an electron into them. Like Pauli's exclusion principle forbids me from doing that. So in that sense, the chemical potential definition will tell me that the minimum amount of energy that I need to have is the highest occupied energy, which is considered as the Fermi distribution. However, for solids, that is not necessarily the case. Why is it not the case? Because in a solid, if I try to add one more electron to this system, I will end up adding it in the conduction band because the valence band is completely filled. So, which of these two values is the Fermi level? Is it the valence band, top of the like EV, the my highest energy of the valence band, because that is the point to which my electrons are filled, or is it EC because that is the lowest allowed energy in the system, or is it something else? So, to answer this question, we will leverage the symmetry property. Okay, so let me draw a slightly different figure in a new slide. Yes, here we are. So I will consider a figure like so. I will only look at one half of my picture because K values are not particularly relevant now. So this is my conduction band. Too sharp. This is my conduction band. And this is my valence band. Now at T equal to 0 Kelvin. So let me try answering this question first. Let me answer C first, then we will talk about parts A, B, and D. In fact, by answering C, we will figure out what D is going to be. So we now have two candidate values for the Fermi level. So the Fermi level based on our understanding and definitions. So the Fermi level can A be over here, like choice one is over here. Okay, or alternatively, the Fermi level can be way down over here. Sorry, E is increasing in this direction. So this is kind of the x-axis of my graph, and I'm going to plot the Fermi level along this direction. Okay, so I'm kind of like flipping the graph by 90 degrees. So there are two possible values. Now remember, when I'm adding an additional electron, the moment I go one electron over the value of EV, it will appear in EC. So the probability of this state being unoccupied is 0 because at T equal to 0 Kelvin, all these states are occupied. And the probability of this state being unoccupied is 1. So that implies, I will write the following, at T equals 0K, f of EC is equal to 0 and f of EV is equal to 1. Is this clear? If anyone has a doubt, please feel free to ask. up to the valence band, all energy levels are filled. So the Fermi function at that point, like at t equal to 0 Kelvin, is going to be a straight line with value 1, a flat line with value 1. So this much I know for sure. The Fermi function is going to be a flat line, oops, all the way down till here. Now the question is, where does it become 0? So now one thing I know is f of E minus EF is equal to 1 minus, or rather EF minus E, right? Yes, not E minus EF. I'm sorry. F of EF minus E is equal to 1 minus f of EF plus E. This needs to be true at all times. Uh, so let me say whatever the value of, so let me write it as this. So f of EF, now this quantity, like the difference, like I know f of EC is 0. So EF plus EF, or rather EF minus, yeah, EF minus EF minus EV, because this quantity is 1, is equal to 1 minus f of EF plus, or rather, no, I shouldn't have written it like that. Sorry. Yeah, I will write it like this. That will make more sense. So in my system, apologies, this relation holds. F of EV is equal to 1 minus f of EC. This is true. Now the thing is, in my system, again remember the Fermi level is determined by the available energy states and the number of electrons. These two things determine what my Fermi level is. Now I know this relationship holds because on the right hand side I have a quantity that is 1, left hand side this quantity is 0, 1 minus 0 is 1. So this equation holds. And there are no intermediate energy levels available. These are the only physically meaningful energy levels that are present. So that implies EV should be EF minus some quantity delta, and EC should be EF plus the same quantity delta, because this is the symmetry relation that I need to satisfy. And I cannot substitute any other energy here because all the other intermediate energy levels are forbidden. Therefore, from this, by just looking at this equation, we can say that uh, like essentially add these two, then I will get EC plus EV is equal to 2EF, which implies EF is equal to EC plus EV by 2. So the Fermi level in truth is going to be somewhere in the middle. Not somewhere, it is going to be exactly in the middle. But even this is not technically accurate. There is one more factor that we need to consider. So remember in this integral I told you like this dE depends on, like I told you this quantity depends on what kind of a system it is. So when I'm moving from the conduction band to the valence band, my density of states may actually change. Like the amount of number of available states may very well change, and they do change. So that is given by like for people who may have studied some device physics and things like that. You know that there is this notion of effective density of states, which tells me exactly how many states are available at t equal to 0 Kelvin. So if I'm considering the notion of effective density of states, then effective density of states at EC in the conduction band may be different from the effective density of states in EV. So the scaling factor, the DE that I must take for the system will actually change when I move from EC to EV. So because of that, there is typically a small correction. You may be familiar with this. So I will essentially have a 4 times square root of NC plus NV squared or something like that. I don't remember the exact quantity, but suffice to say, it is going to be slightly in this neighborhood. But that quantity is never going to be bigger than EC plus EV by 2. It is the intrinsic Fermi level is always going to be somewhere near the middle. It may be slightly above or slightly below depending on the effective density of states. But the takeaway point here is when I have a system with forbidden energy levels, the Fermi level may sometimes lie between two allowed energies. The Fermi level may not be a physical energy level. Okay. So in this state, in this system,
So, sir, it is
yes.
saying about the distribution of energy levels. It's not saying anything about the occupation of electrons like that.
So again, the Fermi distribution does not give me the occupation probability. Remember the Fermi distribution? Yeah, again, you joined late, so you kind of missed this. So it just says the probability that an electron may have that energy. That is all. Whether it actually does have depends on whether there is an energy level present there. This simply tells me if an electron can or cannot have a certain energy level. At t equal to 0, my Fermi distribution is going to be a kind of cutoff function over here. So in this case, I know any energy level above this, I will never find any electrons with that energy at t equal to 0. And from EF to EC, I know those are forbidden energy levels either ways. So I don't need the Fermi distribution function to tell me if I'm going to find an electron or not. The property of the system tells me that those energy levels are forbidden. So what you need to understand is the Fermi distribution actually does not care about the system. It is just a probability distribution. To get the actual occupation probability, I need to multiply that by the energy distribution of the system itself. Like not the energy distribution, the energy configuration, the states of the system itself. And for that, we will need the density of states. Okay,
That
so
EF is equal to EC plus EV by 2. Is that
yes,
the conduction band, valence band maxima plus conduction band
yes, yes,
minima?
yes. I've marked EC and EV here in this figure, as you can see. So this is
Okay, irrespective of where the highest occupied electron
like
is positioned.
it is going to be. I didn't understand. What were you
Like
saying?
irrespective of where the electron highest energy electron present.
At t equal to
That
0 Kelvin.
okay.
Again, this is for a system where
That
only
only
the valence band is completely filled at t equal to 0, and I should also mention the conduction band is empty. For this system, the Fermi level lies in the middle. Again, energy configuration and the number of electrons. If I have a system where at t equal to 0, I have some electrons in the conduction band, then the Fermi level will be inside the conduction band.
okay. Okay.
Like this is the ultimate takeaway point is this. Where is that? Yeah. I have to look at these two. I have to look at both of these at t equal to 0 and decide what my like highest occupied energy level is, or the lowest possible energy an electron may have in order to enter the system. We are going to see how that influences things as we go forward. So now what happens at higher temperatures? At higher temperatures, at
Sir,
EF, the yes. Any more questions?
whether by biasing or by
Can you speak a
perturbations.
bit louder? Like I'm barely
Hello?
able to hear you. Yeah, please. Huh.
Sir, whether by any perturbation like biasing or by electrical magnetic field, these energy levels can modify or
Of
like
course, they can shift, in which case the Fermi level will also shift, which happens.
some people will say that by biasing they will increase this Fermi level up and down.
Yeah, so of course it will change, right? Because my EC and EV have changed when I bias my system. When I apply
Yeah,
voltage to this, the relative energies raise or lower, right? Depending on what kind of a voltage I'm applying. So if the EC and EV themselves are moving, then of course EF has to move.
yes. Then I had this aggressive doubt which like very difficult to
Again, I'm
answer.
unable to hear you. Like, please
Hello?
speak louder. Huh.
Hello?
Yeah.
Yeah, in that case, I actually have a doubt. Till now, I didn't got answer. Like, in if we take like a metal semiconductor junction,
Uh-huh.
a Schottky barrier, a Schottky contact
Mm-hmm.
interface, whether we can trace electrodes or metals Fermi level beyond the Schottky barrier, so electrons can flow from metal to semiconductor. Like people say that the barrier height is increasing always if we apply reverse bias,
Mm-hmm.
but either whether the electrons from metal can go because the metal is kept in negative bias, so it have to cross that barrier and have to transport electrons from metal to semiconductor.
So let me ask you this, like let me answer your question with another question. Since you spoke about Schottky barriers and Schottky diodes, you tell me this, when my Schottky diode is reverse biased, does a current flow through it?
No, sir.
So that there you have it. You have physical evidence to see that electrons are actually unable to pass it because there is a barrier. You've managed
Yeah,
to create
but
a barrier.
yeah, but can the electron? Okay, I got it. But if we write band diagram there, like
Yeah.
people say that semiconductor electrons can cross to metal, but can metals electrons can come to semiconductor?
Okay, tell you
Because
what. Junctions, because the question that you are asking technically doesn't have anything to do with the Fermi level. It has to do with other dynamics, and we are not yet not discussing that yet. I will remember this question when we talk about junctions. When we talk about semiconductor junctions, and especially metal semiconductor or metal oxide semiconductor junctions, then I will come to this. Or if I have some time at the end of this session, I will try to address this question. Okay?
oh, thank you,
Yeah.
sir.
Yeah.
Sorry for interruption.
No, that is fine. Like, don't have to apologize. You're free to ask any question that you want to ask. So, yes, to cap this off, how is the Fermi distribution going to look like at some t not equal to 0? It's going to go like this and drop, and it will come all the way to half, and then it's going to be like this. So, these are the probabilities. Essentially, this does not mean that, oh, yeah, it shouldn't be 1 all the way till the valence band. It should start falling. Oh, God. Yeah, there's one problem with this. It should kind of fall. It start falling below here, but I have real troubles drawing these figures. Yeah, it's going to be something like this, where I have to remember that this is the value 1. So at this point, the value is 1, and at this point, the value is half. So for any temperature, it's going to be a curve like this, which will flatten, 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 and flatten. Like now, I may ask a question. At t equal to infinity, what is going to be the value of the Fermi distribution function? What is the value of this function going to be at t equal to infinity?
One.
No. Come on, look at it. The exponent, this term will vanish to 0. E to the power 0 is 1. So it is going to be 1 by 1 plus 1, half. So,
Sir, yeah.
okay, so let me write that as a small footnote over here. Or, Just a trivia note. At, or I shouldn't say at, because infinite temperature is not possible. So T tending to infinity implies f of e is equal to half. This doesn't mean every level is unoccupied. This means at infinite temperature, so much energy is available that any state may be occupied. That is all. Any available energy state in my system may be occupied, may be unoccupied, because any electron can get excited to any other energy level. So at t equal to infinity, again my Fermi distribution function is going to be a fully flat constant line at value half. And even in that case, this integral relation holds. Integral 0 to infinity f of e dE should be 1. But it's literally a constant line parallel to the x-axis going all the way to infinity. But the integral has to be defined in such a way that that integral comes out to be 1. Okay. So maybe the reason for that will become clear when we go into week 6 of things, when we figure out what the derivative of the Fermi function looks like and what implications it has. Okay, so we have done this. This is over. And the Fermi level we have discussed. So I will write the answer here. It's going to be around EC plus EV by 2. The exact value will depend on the number of energy states actually available in the conduction and the valence bands. Fermi distribution at 0 we have discussed. And the last question, this is, common knowledge. Like essentially, if I have a metal where all the electrons reside only up to the valence band at T equal to 0, then such a material will behave as an intrinsic semiconductor. So that is our situation. Okay. Now, let us say we have a similar system where we have a light doping. Okay. So, what happens when my system is lightly doped?
The Fermi level changes.
Yes, of course. So that's essentially what I shall illustrate here. I'll do it quickly. So when I have a light doping, that means now we technically have to think backwards. So let us say I have my conduction band and I have my valence band. Now assume that there are already electrons in my conduction band through whatever, like, let us say the temperature is high enough that I have electrons in the conduction band. Now, if these electrons need to de-excite and come back to the valence band, they need not uh, they need not have an energy that is EC or below EC. Okay, so let us say this is EC, this is sorry, this is EV. I'm sorry. This is EV, uh, EV, and this is EC. Now, previously, in this case, if an electron had been excited from here to here, then the only de-excitation it can do is come back to EC. Okay, like it can only come back to the next nearest, what to say, like available empty energy level in an intrinsic semiconductor. Whereas in this case, what we have managed to do is we have introduced a small level of acceptor. So I have an EA also. So these are my acceptor sites. Uh, I will quickly give you an idea of why this EA is always going to be above. Or let me ask, why do we always draw EA above the valence band and E donor below the conduction band? Why do we do that? Where do we get that guarantee from that the acceptor level is always going to be above the like valence band? Any ideas?
Like since we added impurity,
Yes.
their valence band or their Fermi level is the EA one.
Yeah, yeah. I mean, that is what we will eventually derive. But how do I know for sure that EA is above EV and not below EV? Where do I get that guarantee from? So the answer to that is actually like relatively straightforward. The idea is whenever I'm doping an acceptor atom, it has fewer electrons to contribute to the bonds in the material than the, like, let me consider I'm doping silicon with so what is a good p dopant? Any recommendations?
Boron.
Yeah, okay. So let me say silicon doped with boron. Hmm. Boron, or even like aluminum, people usually don't do because there are other issues there. Yeah, but boron is a good candidate. So now boron technically, like we know that picture that we know from our high school days, that boron of course has only three outer electrons and therefore only three of the bonds will be there and one of these bonds will be empty. Now when one of those bonds are not formed, I can think in two ways. My electron that is supposed to take part in the bonding has no longer formed that bond. So those electronic states will, so the process of a chemical bond forming is a process of stabilization. So when a bond is formed, the energy of the system will go down. When a bond is not formed, the energy will stay higher than that. So these are the energies of the bonded electrons. EA is nothing but the vacant energy states corresponding to the unbonded electrons, and they will always be higher than the energy of the uh, bonded electron. So it always has to be above EV. Similarly, when I'm considering a donor atom, when I'm say doping it with phosphorus, the fifth electron does not take part in any of the bonding processes, so it is nearly free to move. Here we are actually considering bonded electrons that have a certain higher energy. Now, these electrons, since they are not bonded, they are essentially open electrons. I know that they can achieve free motion at an energy less than EC, which is why the donor level is almost always. Although there are exceptional cases where I can dope atoms where EC kind of moves into the conduction band. That is very much possible. But EV almost invariably is going to be above, unless and until I, build some kind of a heterostructure or some kind of a special system where I'm forcing EA into the conduction band. In most standard doping cases, EA is always going to be above the valence band HEV. Okay, so now if I have an electron over here, if I have an red is good enough. If I have an electron here, now the question is, how can the electron de-excite? So the thing is, or rather, let me say, what is the lowest energy an electron can have to be introduced into the system? It doesn't have to be EC. I can actually introduce an additional electron in the acceptor layer itself. Any electron with energy at least EA can accept an electron. So yeah, I shouldn't have talked about. I shouldn't have spoken about de-excitation. I should have talked about the excitation. So let me say I have an electron that is over here. Now, if this wants to get excited, it is no longer going to go to the conduct. It no longer needs to go to the conduction band as a means of excitation. Excitation probability is non-zero from EV to EA itself. So that is why, however, when an electron enters EA, it is no longer a free moving electron. It is not free to move. It is not a conduction electron. So this will get bound in the EA levels, and the hole that is subsequently formed takes part in the conduction. So in this case, the actual Fermi level of the system is still going to be somewhere over here. The actual Fermi level will still be somewhere in the middle. It is not going to move. However, for all physical purposes, EA will serve like the Fermi level because that is the lowest possible energy a new electron. Let me say I have I have considered this dope material at T equal to 0 Kelvin. Now at T equal to 0 Kelvin, if I want to add a new electron, I don't need an electron with energy EC. An electron with EA is enough. Although it will not behave as a conduction electron. So doping changes the dynamics of the process, which is why when I say T not equal to 0, the Fermi level will kind of get stretched. Like if I'm looking at the curve, previously it will hit half over here. Now what will happen is it will actually hit the half probability somewhere between EA and the original EF, the intrinsic EF. Okay, so my Fermi function is going to look something like this. And because of this, the symmetry is shifted. Previously, in an intrinsic semiconductor, the probability of finding electrons and holes is equal because my point of symmetry is right in the middle. So the probability of an electron being absent here is the same as the probability of an electron being present here. So in an intrinsic semiconductor, the number of electrons and holes will always be a constant. Whereas in this, that is not the case because an electron will jump into the acceptance layer and acceptor layer, and there will be no electrons in the conduction band. Therefore, the probability of finding an electron is not 1 minus probability of is not equal to the probability of finding a hole. Now the probability of finding a hole will be higher than probability of finding an electron. So in that sense, my Fermi distribution will be shifted ever so slightly. Like this point, it is not half. This is not equal to 0.5. 0.5 will be somewhere over here, very close to this EA, which is why this quantity EA, it is not the Fermi level, it is referred to as the quasi-Fermi level. So doping, the takeaway point from here is doping will destroy the symmetry of the Fermi function, which implies probability of finding electron in conduction band is no longer equal to probability of finding hole in valence band. Whereas in the previous case, I shall write this here, probability of finding E minus electron in conduction band is exactly equal to probability of finding a hole in the valence band. So the idea of doping can also be understood in terms of the Fermi level and the shifting of or the apparent shifting of the Fermi levels. So this problem is also done. And from this we can see that the nature of current carriers, I know this is greater and this is lesser. Therefore, in fact, I can say that this quantity is going to be less than half. Therefore, conduction is carried out by the holes. Okay. So with this, we come to an end of our discussion about Fermi levels. We shall look at some more Fermi level problems later on when we talk about modes and other things. Right now, we shall conclude our discussion about Fermi levels at this point. So we are at problem 3, right? Yes. Now we are talking about the ballistic transport model. So this is the beginning of the study of nanoscale devices. So now we are looking at conduction in nanoscale devices. So this model that we have is also known as Landauer's model. So this gentleman was a scientist in IBM in the 60s and 70s. So these are expressions that you might have seen in your lectures already. The stored charge density is given by this quantity, integral. So this integration takes place between, so I will write that here, limits of integration are defined by the operation range of the device. So please do not think that these are indefinite integrals. These are integrals where the limits have not been specified. Okay. So the uh, stored charge is given by this. So in, oh yeah, I should have also done one more thing. So whenever we are looking at this transport model, we are looking at two terminal systems, two terminal devices, and the model is as shown. So I have my source and the drain for electrons and the channel. Our assumptions are this is a bulk material, this is also a bulk material, and this is a nanoscale or mesoscopic material. So this is the kind of system that we are considering. Right now, we are not particularly looking at any bias. We shall look at that in the next week. Mm, So yes, the stored charge is given by, so I will consider this to be material 1, this to be material 2. Okay. So this is the convention that we are uh, adopting. So the current through the channel is given by something and not something by this expression. 2q by h integral gamma of e times pi into dE by 2 f1 of e minus f2 of e dE. So this quantity gamma e is referred to as the energy broadening, and that is given by gamma of e is equal to h bar by tau of e, where tau of e is the transit time. Okay, and this is essentially a consequence of the Heisenberg uncertainty principle, which was I mean, we saw this in week 1 of our session. So this is the Heisenberg uncertainty principle, where
Sir, what is this transient time? Is it different from relaxation time?
yes, transit time is the time the electron takes to go from point 1 to point 2.
Okay, sir.
It is literally the time the electron takes to travel from point A to point B. Now you can ask, it's a quantum particle. How do I know that time? Well, you can think of it like this. Let us say I'm applying a pulse voltage and I'm measuring the current and I'm looking at the time delay between the two. Like how long after the pulse, after I apply the pulse, do I see a pulse in the current? Usually it's going to be a very small number, but that is the whole point here. So gamma of E times tau of E is of the order of h bar. So this is equivalent to delta E dot delta T is to the order of h bar. So this is the energy time uncertainty relation, something that I mentioned that we shall look at. So here we are looking at that relation. We will not go into too much discussion
So
about.
this gamma is like FWHM.
I'm sorry, what?
This gamma is like uh, i- it's energy broadening.
Yes, delta E. It's a change in the energy.
So like FWHM, full width half
No, no,
max.
no, no, no. Okay, we need not consider it as. No, this is not a distribution. So essentially, okay, let me put it this way. Let us say I have a particle of energy E. Okay, I will take some time to explain this also. Let me have a brief word about broadening. Good that you are here in person and you are able to ask these questions. It is likely to benefit others as well. So, what do I mean by energy broadening? So, how should I go about explaining this? Hmm. Okay. Now, let me say I have, so let a particle have kinetic energy, kinetic energy, E. Let a free particle, yes, let me see that. Kinetic energy, E. Now, let us say I'm trying to measure this kinetic energy. Now, when I'm measuring this kinetic energy, how do I do that? One method is I will try to absorb this particle and take all the energy from it. Now, this entire energy transfer, so kinetic energy E. So, let me write the next statement. Measuring the energy value, or rather the value of energy of a particle, I did not even say energy value, energy of this particle will, or cannot be done instantaneously. I hope you can understand this. Because why is this so? Why can I not do this instantaneously? Because when I'm trying to absorb this energy or observe this energy, some information is coming to me. And no information can travel faster than the speed of light. So let us say I'm at some point looking at this particle and I see it moving. I cannot in an instant tell what the energy is. I will have to observe it for a finite amount of time. Like think about it like this. Let us say you are seeing a rocket flying or an airplane flying in the sky and you want to measure the kinetic energy of that object. How will you do that? You will measure the velocity. But to measure the velocity of a particle, I cannot do it in a single instant. Even classically, to measure the velocity, what I will have to do is I will have to take 2 points and see how quickly the object crosses those 2 points. And that will give me a notion of distance covered uh, in a time interval. So after measuring the velocity, if I know the mass of the object, I can get the momentum and the kinetic energy. So I cannot in an instant say what the kinetic energy of a system is physically. Now what the uncertainty principle tells me is, if I perform such a measurement of energy over a finite time period, then I will, the measured value of energy is bound to vary from the actual energy of the system. Okay, so energy measured over time will often be different from E. Okay, so the energy measured over time, let me call this quantity EM, measured energy. So E minus EM is my delta E. Okay, cannot be done instantaneously, which implies, let me say, time of measurement is some tau, or time taken for measurement is equal to tau. Then the uncertainty relationship essentially tells me delta E dot tau is approximately h bar. H bar by 2, h bar by 4, or whatever, like, it is in the neighborhood of h bar. So this will, like, therefore I can never make tau 0, because in that case delta E will become infinite. Like, I will, if I instantaneously try to measure the energy of a particle, I will have an infinite, amount of error. And it's not just error, I can, like, potentially I will be forcing my particle to have infinite energy. Like, look back and think about my discussion, like the discussion that was done on the momentum position uncertainty. Like, when I try to compress a material, the act of compression increases the energy of my momentum of my system, and that momentum opposes this act of compression or confinement. So similarly, when I try to measure the energy of the system instantaneously, the energy will blow up. It's not just a statistical error, it is a physical phenomenon. Likewise, if I want to get a very accurate measurement of the energy, then I will have to measure the system very slowly over a very large interval of time. But that is also not practical. So, whenever we are in the intermediate region, the actual energy of the particles is going to be something other than the initial energy. So, in this case, gamma of E essentially tells me, let us say I'm expecting to find an electron passing through the channel at a certain energy E. But since it is in the channel only for a finite amount of time, the energy itself will undergo quantum fluctuations. And that quantum fluctuation is represented by this energy broadening term. I hope it is clear now. So energy broadening is actually a physical variation. It's a physical fluctuation. It is not just a statistical fluctuation. Energy, or rather fluctuation of energy of a particle in a state with finite lifetime. Okay. Okay, so the next question is essentially to go through the derivations. We still have time, so I can go through this. So first we need to find out the expression for the stored charge and then the current flowing through a ballistic channel. And we also would like to find out what the Fermi energy of the system will be at equilibrium. So first, Again, now no external.
Sir, in what cases ballistic transport can will happen? Like when, what are the conditions it's required
We
to
will come
happen?
to that next week. When we talk about modes, next week or the week after that, we will explicitly go into this. Like when do I have ballistic transport? When will I have like normal transport as given by the Drude-Sommerfeld model or our standard diffusive transport? So that will become apparent once we start looking at the transition from ballistic to diffusive. So there we will be able to identify boundaries where ballistic transport will happen. So you'll get an explicit expression for that. Okay.
Okay, sir.
So maybe the week after next, week 6, we will be discussing that. All right. So now again going back once again to the device model that we are considering, we are looking at the two-terminal device. Now this figure is not to scale. Like this is just for emphasis on detail. Okay, so please don't think that this is the actual length and width of the contact, and this is the actual length of the channel. Okay, so I have source, I have the channel C, and then I have the source S and the drain D. Now, remember the Fermi function is uniform to all of these. That is why I took all that time in the initial half to tell you that the Fermi function will not change. The only thing that is going to change is the Fermi level. Okay. So because the number of the size and the number of electrons present in the source may be different, different from that of the drain. So the Fermi levels are going to change. So I will have uh, an E1, or rather I will say EF1, how have I written it? So I'm writing yes. So I will have an EF1. Remember I called this material 1 and this is material 2. I will have an EF2. Now you can ask what about the energy level, Fermi level in the channel? It is actually not very easy to define the Fermi level in the channel, because when my device is operating, or when it is in, like, essentially the extent to which electrons will be filled into the channel depends on the source and drain, because electrons can now move from the source and the drain into the channel. So a priori, I cannot tell what the Fermi level of the channel is. First, I have to decide how many electrons are present, and that will help me estimate the Fermi level of the channel. Okay. So now to consider the movement, let us look at the direct, like, picture. So in, and let me also assume that these are bulk contacts, and yeah, I will take them to be semiconductors. So I will have some EC and EV. So this is for the source. And my channel I can consider to be a series of discrete energy levels, because my channel is going to be a very small channel, which implies there is going to be plenty of confinement in my channel. Okay, so it is going to be a very short 1D channel, 2D channel, 3D channel, whatever it is, but because of its dimension, there is a great deal of confinement. Confinement automatically implies that I will have discrete energy levels. This is to recall from the sessions from week 1 and week 2. So my system is going to be, a bunch of energy levels like this. And then again on the drain side, I'm going to have another, energy level, maybe less, maybe more. I'm intentionally making it vague so that the figure remains as generic as possible. And somewhere in the middle, I'm going to have EF1. Oops. EF1. And somewhere in the middle over here, I'm going to have EF2. Now, when I put these systems in contact, essentially what is going to happen? The electrons will distribute themselves into the available energies. So let me, so this is the channel, this is the source. Oh no, source and drain I've defined before. So I need to use a different color. So channel and drain. So let me look at the source channel interface. Now the source will try to fill energy states up to EF1 in the channel. Okay, so a certain number of electrons will move in. So, like depending on the energy levels. So that will be given by, so the rate, the flux of electrons. Let me call that F1 is going to be the number of electrons in the source minus the number of electrons in the channel immediately on the source side divided by 2. So that is essentially the rate of change of electron density. Okay, so it is Ns at a given energy minus Nc at the same energy divided by tau 1. So this is the time taken for my electrons to move from the source into the channel. So as soon as I establish this contact, let me say after a certain time, the electrons are getting filled. So this is part 1. Yeah, just 1 second. Let me have some water. Yeah, thank you. And sorry for the disturbance. Okay, the recording is still underway. I'm glad. Yeah. So now the second part is my channel drain interface. Now, right now I have not applied any voltage, so actually doesn't make much of a difference. The only thing that the channel drain will try to do is, since I'm calling it the drain, I will write the statement like this. The drain will collect all electrons with energy above EF2. Essentially, I have EF1 and I have some energy level E. Let me put that down in blue. And I have EF2. Now, an electron will move from the source to drain if and only if at every successive step it is losing energy. Because an electron cannot spontaneously gain energy and achieve excitation. Like this, I'm talking without any biases. So, even without any bias, if I want an electron to move from the source to the drain, it should have some energy below or above EF. There should be an available empty energy state in the channel. So this is an empty state in the channel. And the drain will collect all electrons with energy above EF2. So EF2 has to be further below, lower than this. And this is something that we see from, even a PN junction diode. A current will flow through them only if the Fermi levels, are displaced. So that will give me the direction of flow of the electrons. The opposite is going to be the direction of the actual current. because we look at current as a positive transfer of charge or a transfer of positive charge. Okay, so this will ensure that I can hop from here to here and then from here to here. So the rate at which that is happening is given by, so flux of outgoing electrons is given by minus dn by dt, which is equal to EC, oh no, N of, yes, did I write EC over here? No, I wrote NS and NC, right? Yes. So NC of E minus ND of E divided by some quantity tau 2. So this is where I stand. However, I can assume, now I can make an assumption that source and drain are the same material. If drain are the same material, then I can say that tau 1 and tau 2 are likely to be equal, because an electron going in and an electron coming out between the same kind of a junction ought to behave in the same way. Like, I cannot say this junction is acting like some kind of a one-way system. So again, no bias is present. Like, this is a completely unbiased situation. That is why I'm able to say this. So from this, I can say that at equilibrium, F1 is equal to F2. Like, the numerical values should be the same. So from this, we will get NE minus ND of E in C is equal to NS of E minus NC of E. So from this, we will have uh, NC of E is equal to NS of E plus ND of E. Yes, yes, ND of E by 2. Now I know N is equal to density of states d of E times the Fermi distribution function f of E. So by now substituting the necessary parameters into this, I will get, oh, did I duplicate it? So this will give me N of E is equal to d of E. Since I said it's the same material, density of states is going to be the same. But the Fermi function need not always be the same. Of course, in the case there is no bias, it is going to be the same. But typically, not always going to be the same. Which is why I will write this as F1 of E. Oh no. N of E is given by this, which I wrote. Therefore, NC of E is D of E into F1 of E for side 1 plus F2 of E for, like, this is for the source side, this is for the drain side, divided by 2, which implies the complete charge is integrated over all values of energy. So the stored charge, capital N, is integral d of E F1 of E plus F2 of E divided by 2. TE. And this is the exact expression that we have. Similarly, when we are looking at the current, we can assume that there is a continuity, like essentially the rate of flux, incoming electrons and outgoing electrons should be continuous throughout the material. So using arguments like that, we can derive this expression right here. So over there, we will need to mention what the value of tau is, and that will lead to the appearance of the gamma e quantity. Since we are running out of time and since this has already been done in the lecture, I am leaving this. If you have any doubts, please feel free to post them on the forum. I will address them as and when the questions show up. So this part we have done one half, and essentially you have to use the same reasoning. So I will just write that here. Similar reasoning may be used to derive I in such devices. Now we come to the last part. Again, I decided, modes, because we are already approaching 2 hours, and I don't want to, stuff too many topics. And right now, for this week, modes are not of very serious concern either. So, just like last week, I will tell you, I will give you my, what to say, like guarantee that will be covered next week. All right. So the final problem for the day is the following. Now an electron traveling through a ballistic channel undergoes an energy broadening of 0.01 electron volts. Now we are asked to estimate the velocity of this electron if the channel length is 20 nanometers. Now this is a very nice problem because it will tell us something very important. And I think it may also answer some questions that Hemant, who's in attendance for today's session, has asked. So first, I've been given gamma of E is equal to 0.01 electron volts. Again, when I'm solving numericals here, just because I don't want to do too much multiplication and stuff in front of you, I will take approximate values and do order of magnitude calculation. However, don't use methods like that in the exams. In your exams and assignments and all those things, please use the appropriate constant values, use a calculator and things like that to solve your problems. I want to be done with this quickly and essentially just convey the idea of what is happening. Okay, so first things first, H bar is 1 by approximately 6.28 into 6.62 into 10 to the power minus 34 joule Kelvin. No, is it joule Kelvin? No, not joule Kelvin. Why was I writing joule Kelvin? Joule second. Yes, apologies. Joule second units of angular momentum. Okay, so I will say this is approximately equal to 10 to the power minus 34 joule second. 6.6 to 6.28 are more or less, equal for me. So I will say this is approximately equal to this. Okay. Therefore, and well, we will come to what the electron volt is. Therefore, tau of E is going to be h bar divided by gamma of E. So this will be 10 to the power minus 34 divided by 0.01 into 1.6 into 10 to the power minus 19. So that is 1 electron volt. Now 10 to the power, yeah, so if we do the math, this is 10 to the power minus 21, so I'm going to get 10 to the power minus 13, and 1 divided by 1.6, I will just say it is, approximately 0.6. So this is going to be 6 into 10 to the power minus 14 seconds. So this is going to be equal to 6 into 10 to the power minus 14 seconds. Yes. Wait. Oh, it's not going to be 13. 10 to the power minus 19. Oh god, I made a mistake. I apologize. Or have I? No, 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 I have not made a mistake. So this is 1 by 100, which is 10 to the power minus 2, 10 to the power minus 21. Yes, indeed. So 10 to the power minus 14 seconds. Now this is the transit time. Now what is the velocity? Velocity at this energy V of E is going to be length of the channel divided by the transit time. So this is going to be 20 divided by 6 into 10 to the power 14 into 10 to the power minus 9. So this will give me something like 3.2 by 3. So that's going to be 67 into 10 to the power 5 meters per second, or alternately 3.67 into 3.67 into 10 to the power 7 centimeters per second. Now, typically, when we talk about drift velocities of electron in bulk conductors, so typical drift velocities are of the order of 0.01 centimeter per second. So 10 to the power minus 2 or 10 to the power minus 1 centimeter per second. It is something in that range. So 0.12 or 10 to the power minus 1 to 10 to the power minus 2 centimeter per second. So this is ultimately the notion of ballistic transport. If I have my drift velocities that are this high, that are to the order of 10 to the power 7 centimeters per second or 10 to the power 5 meters per second, then I will say my electrons are undergoing ballistic transport. However, if the transit time, or not transit time, if the effective velocity, the drift velocity of my electron is below 1 centimeter per second, then we will have so typical drift velocities in bulk solids. So in this case, of course, there is no ballistic conduction. So this is the ultimate identification mark. So to sum up, when we calculate the drift velocity, sorry, the velocity, estimate the velocity, I'm not even calculating it. When I estimate the velocity, I get it to be to the order 10 to the power 7 centimeters per second. But typical drift velocities in bulk solids, where I have milliampere or ampere currents, then the drift velocities is going to be a few millimeters or even less than a few millimeters per second. So that's it's actually not very small if we look at the electrons in a solid and the rates at which they move, uh, because there are a lot of electrons present in a bulk solid. So the drift velocities, the analog of drift velocities is going to be typically high. This does not imply my current is going to increase, because by virtue of making my channel small, the number of electrons participating in conduction are going to reduce. So the net current is still going to be more or less where we expect it to be. It is going to be in the milliampere region again. Now, how this kind of arrives at, how we kind of arrive at this value is what we need the notion of modes for. So that we shall do in the next week's session. So with that, I will bring today's session to a close. I thank the live attendees for joining today's session, and also like further thank them for asking questions and making the session interactive. And to the rest, I thank you all for listening to this and hope this was helpful in enhancing your understanding of the course. We shall meet again, same time next week. Let me stop the recording and end the session.